Good evening. I'm Lois Mage. I am the co-chair of the Science and Research Facilities Committee of the AIA, and my team and I are here to bring you our presentation on mass timber and the future of sustainable science buildings, which may or may not be exactly what we talk about. I think that mass timber as a structural material in science buildings has really been emerging for a decade now. My interest in particular began about 8 years ago when I was working on a project at the University of Oregon with my firm, Ennead Architects. We wanted very much to use the material because it felt so of the region, but for all the reasons we're going to talk about tonight, it didn't prove to be a material that was easy to adapt to science buildings for a number of reasons. And so we used the material really more to create both a sort of collaborative environment, a warm space to be in, and really a biophilic connection to the site of the building. I think that as a structural material over the last decade, our industry has really been improving the ability to be able to use mass timber as a structural element in science buildings. And what we'd like to do tonight is to really share two examples with you of science-related buildings, one vibration sensitive, one not. The Manning College of Information and Computer Sciences at the University of Massachusetts in Amherst, and the Princeton University Environmental Studies Commons, and the School of Engineering and Applied Sciences at Princeton. These buildings are similar, yet very different. One being a computational building, one being an engineering building, one having vibration-sensitive spaces, the other not. But I think that in general, the buildings both have some remarkable similarities, which we'll share with you tonight. These are our learning objectives, which I'm not going to read through, which I'm sure you'll be pleased to hear. Maybe you've had a chance to take a look at them online, but a number of the issues that you find in the learning objectives we'll be talking about today in addition to creating a collaborative environment and using wood as a material for its sustainable properties. We'll also dive in probably a little bit more into the building structural capabilities, some of the challenges of using mass timber as a structural material, and a lot of technical issues really focused on, I think, some of the challenges that the material still sees in our industry, which have to do with a little bit of client hesitation and a little bit of contractor hesitation with regard to how to use mass timber effectively. And I think we'll have an opportunity to share some of our experiences for these two buildings that are both nearing completion of construction. And you'll hear case studies for both. So with that, I'd like to pull up our team. Why don't you just come on up. So again, I'm Lois Made. I'm with Ennead Architects, and my team includes Mindy No, Jamie Butterfield, Dan Ahrens, and Matt Dion from a collection from Perkins Eastman and Ennead. Again, two firms that I think are very much interested in helping the industry get over the hump and the concern about some of the uses of mass timber and really bringing it into our world. A couple of I think we'll actually come back to this closer to the end of the presentation, but generally there are a number of benefits that we'll be focusing on tonight, and you can see some of them here. And I think with that, you guys sat back down. Come on up. Well, you want to stay there? Okay, that'll be fine. So we're going to do 2 case studies tonight. One of the Manning College of Information and the Princeton, and we're going to start with Dan's presentation of the Manning project.
Thank you very much. I'm going to actually share this presentation with Jamie Butterfield, who worked on the project. There are actually a couple of you who also worked on the project, and it takes a village for sure. So this is for the Manning College of Information Sciences, and it is the Computer Science Laboratory, which is an addition to the existing building. The project really is the marriage between the college's motto of computing for the common good, basically using computer science for humanity, and our outlook of human by design. And I say that not as a point of branding, but of a point of intersection. And I think that you'll see in the project there are many elements of the project that really were supported by this common goal. So the addition is a nearly 100,000 square foot building. Estimated completion is next month. It's still estimated until it's done. It was, the previous slide said September, now it says October. I think we're gonna get there though. And this is beyond our internal village, the village of consultants, the owner and the builders who put this together. And just to highlight, B+AC, structural engineers, together with a sort of multi-headed client that is the University of Massachusetts Building Authority, which does all of the capital building for the university, and the university and all of their normal shops and people who take care of everything from grounds to security, but also then the computer scientists and their mission and putting that forward. And then the builders, Consigli Construction, their partner who did the mass timber erection, Riggs, and Nordic Structures, who is our manufacturer, supplier, and design build partner on, or design assist partner on the mass timber. Very important. You'll see that coming along. Jamie and I are going to split this.
Yeah, thanks. Jamie Butterfield, design principal with PE. This happens to be my first mass timber building. Dan's an old hat at this, so a lot of those AIA credits that you're looking forward to hearing about are going to come out of his mouth, not mine. But I did want to share a little bit about the building from my perspective as kind of a novice to this. And the Chancellor's statement here really set the table for a process with a state institution, a public building, that was a success. Without the sort of commitment at the highest level, we would have, I think, struggled to win the project, because we really came with a degree of expertise, not just in computer science, but also in sustainability and mass timber. But also, once the project was sort of underway, without like facilities on board, right? Without a user group that will talk about computing for the common good, their ambitions for this building ended up being really aligned with the sort of look and feel of a mass, even though they didn't understand what it meant, they kind of had a sense of what it might look like and what it might feel like to be in a building that was made of wood. And they really liked that. And they actually helped steer an interior design process and actually an overall design process that never lost sight of that. And one, maybe I should answer that. Like one of their chief ambitions for the project was to create a place within their organization that felt like home to them. I mean, they had been on campus for quite a long time. The existing building that this is attached to was built in 1999 and has none of the features that are sort of listed here as principles, whether be they sustainable or be they about a convening environment that felt like it was connected to the future, the challenges that we face globally. So a sustainable building that achieved those aims was something that they were really interested in providing. And the program that the building offered was one that I think many architects in the room, how often have we gone into a project thinking, wouldn't it be nice to have a big atrium? And then we kind of know that's never going to happen, so maybe we'll get a two-story space. We went through a value engineering process here and kind of wondered whether or not we were going to hold on to the images, you know, you've seen it, but the large multi-story space that connects 5 floors of program in a meaningful way and manages a very aggressive type topography. But they wanted that. Like that was actually what generated the program for them, was a convening space. And actually in the building, it's sort of that convening space that is the one that celebrates, for the most part, the look and feel of mass timber on the interior. For the state institution of back in when the chancellor made that commitment, across the state, of all state institutions, the university system, the college system, was the poorest performing environmentally. They had the highest energy profile. And amongst all the buildings in the state system, the Manning School of Computer Science was the worst performing building. So this building, which they set out to have net zero low carbon emissions, was going to be attached to a building that not only didn't provide an interior environment that spoke to the needs of the computer science department, but from a performance standpoint, was the worst performing building in the state. And for them, this was the first building coming out of the ground that was abiding by the chancellor's principles. And there were a number of sustainable agenda items, but some of the ones that we struggle most often to convince clients to provide, for example, mass timber, but also like an electrified building connected to a hot water loop instead of steam. Like these were ideas that facilities was on board with right from the beginning. We didn't have to fight with them. We came out of the interview kind of convinced that our pitch to provide a mass timber building that was net zero was aligned with their thinking. So it was not a heavy lift, and dealing with state agencies, that was kind of a pleasant, I think, surprise maybe. The challenges that we faced on the project had more to do with the site issues, like the formal geometry of what we had to squeeze this building onto a site that didn't kind of lend itself to the geometries that you kind of anticipate would be necessary for mass timber. You can see here the plan is kind of this weird trapezoidal. The orange thing is our building, and the blue wing is the 1999 building. So we had a weird shape, and you'll see in the beautiful Princeton building in a moment the rational approach to providing a laboratory design out of mass timber, which abides by sort of a more regular geometry. Here we were trying to deal with the fact that the building didn't really make that an obvious solution. In terms of the siting, like we were connected to an existing computer science building. The building kind of opens up to another location. And the building sits on the northern part of campus, so the main address to the building faces south toward where people are really coming from. The way we solved the problem, at least we did our best to solve the problem of the weird geometry with the need for a convening space by creating this sort of gesture that you move through the building along that diagonal, which helped rationalize a bar to the east, and centralize this convening space, which became the multi-story atrium. I won't detail the plans, but on the lowest floor where you occupy the atrium, is really sort of a conferencing center. So there's an auditorium, there's the colloquium, there's meeting rooms, and then there's the large sort of flexible meeting zone, that sort of triangular space, which is the heart and soul of the building. And then as you move up, this is kind of like a typical floor where you have the research labs, the 3 sort of labs on the right with officing. And then in the little triangle bit over here, we have experimental labs and we have a fabrication lab. And those were sort of the featured, celebrated spaces where research was a little bit more on display. I'll just go through these quickly. And then the building exterior, it's kind of, we were trying to play with the idea that when you enter the building, you're like, wow, it's like warm inside, and you get to see, the timber is kind of revealed. From the exterior, we didn't have a lot of opportunities because of the low energy approach to the design to fenestrate the thing wildly. So we really sort of zoomed in on the main entrance, which is in the middle between these 2 wings as being the glassy bit. But the overall transparency of the building was limited to below 40% to achieve the energy profile that we needed. And we put the glass where really it was mapping not just to the interior social experience, but also kind of where you got to really appreciate the mass timber component. So that gives you a broad overview. Now Dan's going to entertain you with all the fascinating details.
Well, that was pretty entertaining. Just one correction, the window wall ratio is about 30% or less. So just in case you're dialed in, which you should be, to window wall ratios. So another thing to note, and this starts to be very important for mass timber, and how we ended up with a hybrid system. The space that Jamie was talking about cuts through, basically looking from, in this case, the north to the south, from a lower level to an upper level. And that combined with the large spaces that were to be at the lower level, and one more to add is the mechanical space, we had some long span spaces that also needed to align with the existing building. So we had very limited, like, floor to floor heights set by the context. And so here you see, looking east with north on the left and south on the right, how you traverse through that public space, looking at the bar. Every element of the section is working to make this a passive, well daylit space. There's an indication for ground source heat systems. This is an all-electric building. What was really interesting that the university did was to take that out of our project. Please give us like $20 million or something. Put that into a district plant and make the whole area around the building more sustainable. So that was pretty neat. We also designed from the outset a passive design that had solar shading to go with the 30% window wall ratio. The university, feeling that they had tested this out as a prototype, let's use electrochromic glazing. We can use this dynamic glazing and get rid of the solar shades. We said, okay, and we did some studies of daylight and glare, and we adjusted from solar shades and looking at the glare to an improved situation with the dynamic glazing that didn't have exterior solar shades, which was great. We were excited until this was bid out, public bid, and between the acceptance of the bid and the shop drawings came the bankruptcy, and we were left without electrochromic glazing. So let's go back. So then we had to go and redo these studies, adjust mechanical, but we couldn't put the shading back on, if you're wondering about that, because we had also purchased the unitized curtain wall with the right support for electrochromic, but not for solar shading. So that was just an interesting experience. All of this while trying to figure out how to connect this to the edge of CLT decking, which we had from the wood. I don't want to just zoom in on the wood without saying that one of the the goals here, and that image of approaching the building with the biophilic best practices stormwater infiltration was connected to a roof. There's a blue roof, which slowed down the stormwater going to civil, reduced the civil infrastructure by 30%, and caused no strain on mass timber. So free system, no reason not to do it, doesn't impact the structure, reduces civil infrastructure. So something that's a neat trick that we're doing and sharing with you. And so here's the stormwater infiltration system beginning here. Also a big move for accessibility and universal design, very important part of the whole look and feel of the building. But getting to mass timber then, this isn't an all mass timber because the building slopes and also because it sits right up against the existing building and is thought of by code as a different building. It has a 3-hour separation between them. The best thing to do there was, because it has to be self-supporting, is to build this concrete wall. The best thing to get the floor-to-floor heights at that lower level was to use steel. And so we ended up with already a hybrid before we get to the first constructed level of concrete and steel. Above that, it's all mass timber, the labs, the offices, everything else. It's all glulam together with CLT. And we're going to hear about another kind of decking that can be used in the next presentation. The bar, the only regular part of this whole building, is designed to be flexible and adaptable. So we have the basic element of the slab is this CLT. It's 8 feet by 52 feet. It could have been 65 feet. And it's thought of as in bays of 24 feet, which also makes some very good lab bays. Now they don't have wet labs, but they have a lot of flexibility for other kinds of lab setups. The hybrid structure took an inordinate amount of time and quite a bit of time off of my life in terms of getting this done. We have the structural engineer together with a design assist for the mass timber. And neither of those, the steel isn't hard, the concrete isn't hard, but the connections between them were difficult. And so many of them were unique because of this geometry. So it can be done. It's proof of concept that it can be done. I wouldn't recommend doing it like voluntarily in this way. Because you can see the geometries, we have some cantilevers that created other complexities that we wished upon ourselves. So it's really quite interesting. But what's amazing about this is that the construction, the timber went together and not one beam had to be modified. It all slid into place and you can see how tight it's, the tolerances are way tighter than steel. Way tighter, it's amazing. And so, on we went. A couple of things to point out here. One is on the right is the 5-layer cross laminated, meaning every other layer switches, timber beam, slab. Those are the planks that I was talking about. And then the beams, which are set on steel, but the steel is embedded in wood in our case. And we'll look at another case of that coming up. So unitized curtain wall, I'm not sure how often it's been put on a CLT structure, but not that often. So we're all learning together about that and some of the connections. It's also a factory mutual project, and so they're very stringent about how is fire stopped and all of these things. You can see another little bit of hybrid, which is the beginning of braces, these plates that are set into the beams. Those take rods that create diagonal bracing where we didn't have concrete. And every hole in the CLT is pre-designed, pre-cut, came to site like that. And there were no holes cut on site. So there's a lot of coordination that goes on around that compared to a typical building that is a little more flexible. And when we think about science labs, it's an interesting question to raise about the flexibility and the future life and how that happens. So here on the right again, a hole for one of very few floor boxes that we had. Everything else came overhead. And then this is a temporary cover. One of the interesting things, I thought I had a picture of it, but I don't, is that there are steel straps that tie some of these together to add additional support laterally for the CLT. So a little bit more on the design progress here, where we're getting all of the systems. The floor of that entire atrium is radiant heating by ground source heat pump. It's low temperature hot water, high temperature cooling. So this is a cooled radiant slab. So when you come in the summer, it's going to feel really comfortable and cool and warm during the summer. It has to be coordinated. You can't drill through that. Here are some of the fire stopping details where connections between the slabs and the curtain wall happened, all carefully insulated to create a good building envelope. And then finally, almost back to the chancellor's requirement, which by the way came up between the RFP and the interview. So good thing we were aligned, lucky us. But his declaration had to do with operational carbon. Operational carbon is the stuff for heating and cooling and power. It didn't have anything to do with mass timber, and I was reminded by that by the vice chancellor when we presented our schematic design, and there was, in that case, not like full, oh yeah, we've got to do this, but how much does it cost? What's the impact on schedule? And where is that in the whole budget? So that was a bit of a challenge, like most projects have, whereas UMass was sort of on board with a lot of things. But the existing building operational energy is 320 kB2 per square foot, and it does about the same thing that we're trying to do here. This one's 30, so 1/10 of the energy of that existing building. And then the carbon is reduced by nearly 60%, and the vast majority of that is in the structure, the mass timber. And we did extensive studies of the embodied energy and those declarations in terms of studying and modeling the carbon. Interestingly, I mentioned the electrochromic glass, which is very good operationally, was really bad in terms of embodied carbon because of the first impacts of new factories doing new things. So it's a story for maybe afterwards, but here we are. You can see that the entire wood structure went up between June and September last year. Was very beneficial to the schedule. And we're almost there. So there'll be a sort of biophilic place for the students come October, definitely by November. So, Matt.
Good evening, everybody. My name is Matt Dion. I'm with Ennead Architects, project architect and associate principal. For the past about a decade at Ennead, I've been focused on higher education laboratories, including at University of Michigan, NYU Langone Health, worked on a project with Lois, New York University, and most recently, Princeton University. We're going to be talking about the Brigger Hall Commons and Seas project. And just a note on the title of the first building, it's called Brigger Hall. Here you probably saw it referred to as ES or Environmental Studies. Burger Hall is named after the Burger family, who was very generous with a donation recently, so that just changed. As far as I know, the Seas project is still looking for a donor, so if you're interested, I can pass that along. So I'm going to do a quick project overview. We're going to look at the primary structural systems because there's more than just mass timber in this project. Then we're going to focus in on mass timber. We have a few unique assemblies that I want to review with you, and then just some mass timber considerations, lessons learned. Right. This is my first mass timber project, but it's not the first of any yet, certainly. So like Dan, I just want to acknowledge the tremendous team that worked on this project. It always amazes me how many people it requires to take a project from concept to completion. It's really amazing. Just to highlight a few, Lyra, the structural engineering firm, it was an incredible collaborative effort with Lyra. I mean, really, we couldn't have done it without them. Their input and design was paramount here. And actually, Mike Hopper, one of the lead structural engineers, is in the audience today. So Mike, thanks for coming. If there's any questions during the Q&A that are of a structural nature that I can't answer, I may call on Mike to help. In addition, we have Atelier 10, who did the lead sustainability, energy modeling, and all the life cycle cost analysis. On the construction side, we have Whiting Turner, which was the CM, Structurecraft out of Canada, they're the mass timber contractor, and then Haschlacher Norica Timber out of Austria, they're the glulam manufacturer. And just one more I want to add here, I don't want to forget, I mean, some of us have been on this project for over 6 years, incessant deadlines, late nights, weekends. We could have not have done it without the support of our families. And I don't say that only because my wife is in the audience, but I think it's very important to acknowledge our families. This is a tough profession. It takes a lot of time. Some of the value propositions, I'm not going to go into all these, but these were established early in the project with all the stakeholders and the user groups, and these were really our guiding principles as we designed the project and took it from concept through construction. It is intended to be a very flexible wet lab building, and I'll talk a little bit more about the program in a minute. So this is the overall campus. If you're familiar, our site is 17 acres. It's a huge site. It's really big, and it's about, you see that little dotted line, it's about a 15-minute walk from the Princeton train station. Some of the existing things on campus or on the property that we had to remove, there were a series of parking lots, there was some small residential halls, but most interesting is we had to move 2 historic buildings across the street in order to make room for this project, which was really interesting. It's just north of the stadium and south of the eating clubs that are on there on Prospect Avenue. And you know, this is a mass timber project, but there are several projects that are either nearing completion or still under construction that are also mass timber. So Princeton was really excited about using mass timber on this project, and we're seeing it in a lot of projects on their campus as they move forward with their next capital plan. So the Art Museum you may be familiar with, there's the Frick Health Center, and some residential halls are also using mass timber. So if you get a chance to go there, just taking this walk, you'll see a lot of terrific new projects on campus. I just want to mention that NEAD was also hired to do the master plan prior to the concept through construction documents for these projects. So what was really important here was looking at just not ES, environmental studies, and the School of Engineering and Applied Sciences, but also all these other engineering program that they're considering doing as part of their master plan. And the next capital plan is already starting construction on the MAE building, which is just the southeast corner of our site there. So what was really important here was, as we were looking at the entire area here, was the connections through campus, right? Students they have to get from one place to the other, right? So it's really important that we just didn't plop a building down there that would really disrupt that flow. So that was really critical. And also the landscaping. I mean, JCFO is a landscape architect here, and the landscape is really just as critical as the building itself. It was such a big site, it was really important to create these very intimate and unique landscape opportunities in between the buildings and around the buildings as well. This is a rendering. This is an aerial view of the overall project. Dan, do you have your clicker? Does this do a, oh, it does. Excellent, sorry. Okay, so here's the stadium, right? There's the eating clubs with Prospect Avenue up there. This on the south is Ivy Lane and Western Way. So these are a series of several buildings here. This, what I'm circling right here, that's Burger Hall. So that's the Environmental Studies building. The Commons building is right here. The C's project extends to the east, and that includes the BioE building or bioengineering. And then the chemical and biological engineering extends further up to the north. Same diagram, just graphically showing what these represent. So Brigger Hall, 318,000 gross square feet, 5 stories above grade with a partial basement. The primary occupancy is B, so this is all non-production laboratory, which is pretty typical. And it's a type 3A, it's fully sprinklered. Same with the C's building, which includes both BioE and CBE. That's 311, so slightly smaller, but same setup, 5 stories above grade with a partial basement. Also, primary occupancy is B, and it's type 3A. Commons is the unique one. That's only 45,000 gross square feet, just 3 stories, and that's primary occupancy is assembly, but also type 3A. So just some of the program that is within these buildings. Brigger Hall and C's are very similar in that they have teaching labs, lecture halls, multi-purpose spaces. ES includes, or Brigger Hall includes a vivarium as well. On the upper floors, you have typical wet lab, and we'll see some floor plans in a minute, as well as support spaces. We have offices for the PIs, group desks and collaboration spaces for the students, large collaboration areas. We also have an atrium. Unlike Jamie, I do not like atriums. As a project architect, they're incredibly difficult to pull off. We did it here, but and you'll see some images of that in a moment. Commons being assembly space includes a library, large multi-purpose room, a cafe and servery, some other support spaces, and then C's, again, very similar to Brigger Hall. The exception with C's is all the way in the north, there's what we call the theorist pavilion, which is all just dry research and theorists. So, really big site, right? 2,000 feet, basically, from end to end. So depending how fast you're walking, 10 to 15 minutes to get from ES all the way up to the north at the Theorist Pavilion. What we wanted to do here, though, on the first floor is make sure that they were all easily connected. So we called them shirt sleeve connections. So when the weather isn't cooperating, we want students to be able to enter the space and walk from ES and make their way through Commons and into BioE and CD, and really to encourage collaboration between these departments, certainly, but also just make it easy to get from one class to the next. Also just want to mention that there is a small loading dock on the ES side that serves the vivarium primarily, and then there is a central loading dock here along this new street that we connected here, and that services the entire area. So not only is there a public front of house continuous circulation, there's also a service corridor that connects all the vertical transportation in those 2 loading docks. This is Princeton's Sustainability Action Plan, and we don't have to go through each one, but I think you'll see that they're probably very similar to our own firm's Sustainability Action Plan, whoever we work for. Certainly they're very similar to what NEAD strives for. The big one here, reducing their campus greenhouse gas emissions to 0 by 2046. They're primarily doing that by the creation of a geo-exchange facility. So there's boring sites and heat pumps scattered throughout the campus, and the Princeton project, ES&Cs, is taking advantage of that. I'm not going to go into detail, but if you're interested, if you just Google Princeton Geo-Exchange, they have great stuff on their website. They explain it in detail, how it's different from geothermal, and how they're really using it throughout the campus. It's really exciting, and we were able to take advantage of that. Some of the other things, no surprises here, right? Reducing our water usage, stormwater management, sustainable transportation, especially on a big campus like this, reducing waste, developing responsibly, certainly, and then cultivating healthy and resilient habitats. And that has a lot to do with the landscape around the buildings as well. Atelier 10 put together this sustainability slide. I'm not going to go into all of it here, but it just shows all the strategies that we're applying to the ES&C's projects. Just want to note that this is a LEED version 4 for new construction. It's a gold target. We are filing these projects with LEED together, so all of this will be under one filing. We're still on great track for gold. The other thing I want to mention is we looked at a lot of different life cycle cost analysis bundles, both quantitative and qualitative. And the one I just want to point out here, we looped these 4 together, including vegetated roofs, which you're seeing on the, which you're seeing on the top of Commons and also scattered throughout ES and C's. Mass timber structural system, which we're going to focus on today. Natural ventilation in the non-lab areas, in the PI offices and the student workspaces. We do have triple glazed operable windows, which has its own challenges because we have a chill beam system. So those windows are tied to the BAS, so the chill beam can turn off if the window's left open, so we don't have condensation. But it's really terrific opportunity for PIs and students to control their own temperature and rely on natural ventilation. and reduce energy use with the overall building system. And then lastly, stormwater and clear water collection. Again, with a site this big, that's paramount, absolutely critical. This is a typical floor plan of ES, and you're seeing commons here too. So just a quick note on some of the colors. That yellow, that's our primary wet labs. So you're seeing here on the north, switching to the south, and then back here on the north. So Jamie mentions it's a very regular structural system for ES, but we did simple moves with the geometry just to break it up. If you can imagine this being just a simple long bar, it would just appear endless, right? So we created these changes in geometry and then took advantage of those spaces by creating open collaboration spaces and things like that. In between these bars, we have these areas here. This is a non-atrium, but it's a multi-story space. This is the dreaded ES atrium. And then opposite of the labs you're seeing in blue here, that's all the researcher offices, student desks, things of that. In the red color, those are conference rooms that are scattered throughout. Some big other open or lecture spaces. And then in commons here, this is the primary library floor, so this is level 2. And here you're seeing just a glimpse of C's, but a very similar program diagram. Okay, cost and schedule. I know you're all interested in cost. So Brigger Hall and Commons project, $410 million. That's all in construction cost, including site work. C's was $378 million. The cost per square foot was a little higher on C's because we had a higher percentage of lab program versus non-lab. A note on the schedule here, you can see the programming and master plan and concept phase there. We started in third quarter 2018. What was interesting that happened that at the end of the master plan phase, which included concept design for the entirety of ES and Cs, Princeton threw a little curveball. Originally, we had just included BioE as part of phase 1, which included ES and Commons. They decided, you know what, let's do CBE in phase 1 too. So we redid concept design for Cs, and that's when the building split. So originally we had intended to document this as one single project. Instead, because of this change, we created this nightmarish Pong match between deliverables as we went from SD to DD to 50% CD, 85% 100%, right? It was pretty nightmarish. It was a lot of deadlines back and forth, but that's what was needed to be done. The project itself went in front of the Princeton municipality as a whole, and then we broke these up in terms of a filing strategy. So ES and Commons filed under a single TCO, and then C's was a separate TCO. The other thing I want to mention right here is based on the 100% DD documents, Whiting Turner put out a bid for design assist for mass timber, as well as curtain wall and greenhouses. But for mass timber, it was bid to StructureCraft, Nordic Structures, which I believe is UMass, and then Structure Fusion. And I'll go into why, but StructureCraft was chosen for the design assist role. They came a little late, I'll be honest. It would have been nice to have them involved a little bit earlier in the process. I think that could have helped develop things a little further, but in the end, they were a terrific partner, and they really got us to where we need to be. In terms of TCO, ES and Commons has their TCO. They're in move-in right now, and they're trying to get substantial completion. TCO for Cs will be in about a month with substantial completion towards the end of the year. So almost there. This is a recent photo provided by Drone Deploy, a company that Whiting Turner hired to take a lot of aerial shots. This was taken just, I think, 2 weeks ago. So you're seeing, again, ES building here, Brigger Hall, Commons, BioE, and then CBE. This area here on the site, that's been earmarked for a future building. That was part of the master plan. We don't know what that will be, but we'll see where that takes us. Okay, primary structural systems. We have 3. No surprise here, we have reinforced concrete. Obviously for those partial basements, anything below grade. The site actually slopes from the south to the north. There's about a 20 feet elevation change. So the rear side of the first floor is all buried. There was a really large supportive excavation wall, permanent SOE wall as well, that Lyra designed and put in. So we have below grade reinforced concrete. We have post-tensioning. Our entire podium is concrete, which I'll show some diagrams in a minute, but a lot of post-tension beams, which allowed some really great spans and some column transfers from above, which was really helpful. And also, similar to UMass, we have concrete shear walls. Not pictured here, we had some architectural exposed concrete. We had some cylindrical columns on the ground floor as part of that public circulation that I mentioned before. Really beautiful concrete. The middle here, no surprise, structural steel. So, and you'll see in the diagram in a minute, but primarily used in all the laboratory spaces where vibrations were really a concern. On this image here, you're seeing the end of BioE. We took advantage of steel for some really large cantilevers. Down here is a typical structural bay at Brigger Hall. If we had time, we'd talk about this really terrific beam detail that Lear designed, but we'll save that for another time. And then up here in the upper right, this is showing what we're going to be talking about, which is the diagrid structure. These really terrific slender columns that then pick up some glulam diagrid. I have some great pictures of that. And of course, mass timber, glulam, column and beams, very regular grid here. You're seeing another image of the glulam with a DLT above, and I'll go into DLT in a minute, with some double height spaces. And then here's just an enlarged image of the diagrid that we'll go into. This is a really helpful diagram just to understand where are we using mass timber. So this is a wet laboratory building, which you wouldn't think would be appropriate for mass timber, right? We have highly sensitive equipment. We're talking about mass spectrometers, microscopy, a lot of heavy wet lab research, right? So we didn't use mass timber in the labs, right? We looked for opportunities where we could use it. Again, Princeton was really on board from the beginning, and we got additional funding from their sustainability killing to use mass timber. So it wasn't a struggle to get into the project, but it was really determining where is its best use. So I just want you to take note of the colors down here. This darker orange, that's mass timber at a 2-hour rating. I'll talk about why that's important in a minute. The lighter oranges, the colors, those are those big kind of non-atrium and atrium areas. Those are just 1 hour rated. And then the steel is in the gray, these gray bars. And then commons itself, that's the diagrid. So you see in this image here on the bottom right, we have concrete podium, reinforced concrete podium. You can see here where it's buried below grade on the north side. Large transfers to accommodate the different sorts of program on the ground floor versus the upper floors. Steel being used in the primary lab zones, and then timber in those office zones, student zones, and then timber also second floor and above in commons. This may be of interest to some of you that work in laboratory projects typically, the term laboratory suites. So depending on what jurisdiction you're in, it can be defined differently, but for New Jersey, this was filed under 2018 IBC New Jersey edition. Laboratory suites. A laboratory suite can contain more than just a laboratory, so it can contain offices, workstations, bathrooms, whatever you need it to be, as long as it's separated from adjacent construction by a 1-hour fire barrier, and the floor slab is 2 hour. So remember I mentioned that zone of timber being 2 hour, right? This laboratory suite contains both steel and timber. So it was critical and required that this timber be 2 hour rated. Within that laboratory suite, each one, there's a maximum allowed number of quantity of chemicals that can be stored. And that'll depend on what level you are in the building. It reduces as you go up in the building. In the areas outside the laboratory suites, like this area here or this area here, we're able to reduce the rating to 1 hour. Why is that important? Because we could reduce the size of the timber. We could save money, right? So the columns and beams got smaller, the DLT could be reduced, and we found cost savings there. So that was really beneficial. Taking a look at the laboratory module, which is incredibly important. It seems very fixed, but this is actually what allows us to be really flexible with laboratory planning, right? Creating this. So these are based on NIH typical standards, either 10'6" to 11 feet. We use a 10'6" grid here. You can see here, this is Brigger Hall on the left and BioE on the right, very similar. So you have 10'6" by about 30 feet. You're seeing this is the wet lab zone. In Brigger Hall, that was all just one bay. So we either broke up open laboratories here, you're seeing a large open wet lab, and then smaller rooms here for either controlled environmental room or other these smaller support spaces. The corridor itself, this is timber south of this line here. So this is a timber to steel connection. And then timber 8'7", so a very short bay there in the corridor. This is where we ran all of our utilities serving these labs, right? So everything serving the labs, we kept out of it. All of our valves would stop at these lab entries, so everything could be serviced outside of the lab. And then south of here, this is your office and workstation zone. BioE similar, except that you have about a 26-foot bay and then another column grid here at 14'6". This was really tight here, so this is where we typically located support spaces such as microscopy, things like that, tissue culture, things of that nature, and then keeping really the lab as open as we could along the entire facade. Intersections. I'm just going to pause here for a moment. As exciting as mass timber and steel and concrete on their own, I think the intersections are just as cool, right? So the image here on the left, this is at Brigger Hall. You're seeing steel here. You're seeing one of these atrium areas with all the mass timber, the glulam columns and beams, and beyond that, a really tall shear wall, reinforced concrete. Really exciting. Interesting note here, any steel that was close proximity to timber was primed. It's this green color. Mike and I joked that we liked the green color and we should have left that exposed. It was pretty nice. Middle image, this is just a great shot of seeing the steel bar versus the timber bar. And here you're actually seeing them laying out some of the diagrid members for Commons. And then in two instances, both in the Commons building and in the Theorist Pavilion, we had a hybrid structure. So similar to what Dan and Jamie were talking about. In this Theorist Pavilion, this is steel with DLT floor planks, and this is all intumescent fireproofed. With Commons, which we'll talk about in a minute, the diagrid, steel posts with these steel picking up these very large glulam planks that create that diagrid structure. Okay, mass timber assemblies. First up, dowel laminated timber. So what is DLT? I brought a sample here. It's really heavy to pass around. You guys, everybody can come up after and take a look at it. So dowel laminated timber, what's really attractive about DLT is that it's all wood. So CLT, you're gluing those sandwiches together. NLT, you're nailing them together. Right? DLT, all wood. So it's a standard 2x, it's going to be a 2x6, 2x8, 2x12, right? And then it's simply sandwiched, drilled, and then this is inserted, and it's a friction fit. Pretty cool. What's unique about what StructureCraft offers, and one of the main reasons why we chose them, is their DLT, they offer an acoustical profile on the bottom of their DLT, that's what you're seeing here. So this kind of squishy material, that's basically just acoustical ceiling tile. Why that's helpful is that we wanted to expose as much of the DLT as we could. But this being a laboratory building, most of the other surfaces are just really reflective, right? So think of this atrium area. You have wood, chipboard, polished concrete, glass storefronts and offices, highly reflective, right? We need some absorptive material. So that gets you an NRC value on the ceiling of 0.7, which is pretty good. Typical acoustical ceiling tile, you can get up to 0.9, 0.95, depending on what you're specifying. So 0.7 is pretty good. We did that in a combination with fabric wrap panels on the walls. So a combination of that, we were really able to get the acoustical values that SMW or AccuStation was recommending for some of these spaces. So that's what's really unique about a DLT. You're just seeing some image here. This is at StructureCraft shop in Canada. They're just showing how they're rigging up these panels. This is an image of the dowels and the machine they're using for inserting those dowels. These were the first two panels, DLT panels, to go in the project. And this, you're seeing a glulam beam that's attached to some reinforced concrete. I want to point this out because you see this gap. Wood, we know, needs to breathe and needs to move, right? So you need to accommodate these gaps. And in some cases, we were able to locate these joints over a beam. So think about that office section where we have those regular spaced columns and beams, we could hide it. In some cases, we couldn't. So it's important just to understand that when you're looking up here, you're going to see a regular pattern of these acoustical profiles, but in some cases, you're going to see a larger joint. Now, once you put on the slab above, it just appears as a dark shadow line, but just something to keep in mind. The other thing I just wanted to note is the typical kind of makeup here. So here's the DLT with the fibrous insulation with the acoustical profile. We have a layer of 1/2-inch plywood that has a protection membrane, which you'll see, and then 3.5 inches of concrete over a slip sheet. And I'm going to come back to that 3.5 inches in a minute. Just some other images of DLT. Over here, you're seeing that office bar. Here's that corridor. That's that 8'7" grid, right? What we did here, again, to save money, is we reduced the grade of the DLT because we ended up putting an acoustical ceiling tile throughout the entire corridor. That's where we're running all those utilities that I mentioned earlier that are feeding both the offices and the labs. So we reduced the grade to save money, and we got rid of the acoustical profile. We didn't need it, right? No need for it. But what we did, and depending on what jurisdiction you're under, and just make sure you're looking at your current codes, as soon as you conceal mass timber, you typically have to protect it. So you have two options. cover it with chipboard, or fire protection, additional sprinkler coverage. So for us, Whiting Turner looked at both conditions from a cost and schedule perspective. Because we were already running sprinkler lines throughout the corridor anyways, they just added upright heads, and we were good to go. So it wasn't a dramatic increase in cost. This middle image here, you're seeing one of the atrium areas. They're putting this up, and this really went up super fast, right? It was pretty incredible to watch. But you're seeing that protection membrane over the DLT. And then here is another unique detail I want to mention. So because of these gaps, if you can imagine a wall that's perpendicular to this, sound is going to jump, right? So you got PIs that really want a nice quiet office, and you have a group of students working in a group desk room all staying quiet and studying, and you have sound transfer. So what we did was we removed the acoustical profile, they inserted a standard lumber just blocking, and then your top track of your wall was up against that, and that blocked the sound transfer, which is pretty cool. Now, you had to know exactly where those walls were going to be, and thinking about future flexibility, if that wall comes down, is something to consider. But for us, the areas where we have these offices, these are in those larger open areas. They're only going to be offices, right? So we were able to nail that down, which is great. Glulam, next, in terms of mass timber assemblies. Just a note on material, we had really hoped to get Doug fir, beautiful wood, right? Looks gorgeous. It was cost prohibitive. So we ended up doing European spruce for the glulam, and spruce pine fir, also known as SPF, for the DLT, and that helps save some costs. And really, it's still very incredibly attractive. You can see here in this image. So glulam column beams, all the mass timber to timber connections were designed by Structurecraft, right? And because of that, in New Jersey, they had to file what was called a deferred submittal. So they actually had to file their drawings for submission to the HJ for approval. So we just had to consider that as part of the regulatory process. Here, I just want to point out, here's a pretty large column, a similar base detail to what Dan showed earlier. I think it's pretty typical. But one thing to keep in mind is bracing. So this bracing creates these three little holes on each side of the glulam that have to go back and filled and sanded, right, to make sure it looks good. And the other thing to keep in mind is this. We have polished concrete throughout most of the project. We had hoped for terrazzo, but that was VE'd out. I think it was a mistake. So just something to keep in mind. So for these, they had to go back and patch and fill those holes as well on the floor. So just something to remember. You're seeing just a typical image of a base condition on some of those smaller columns, and here kind of a typical just connection that did not require necessarily steel. Here you're seeing some plugs, and we'll look at some other details that show that kind of steel connection. Just some images, again, just showing some of the different geometries here. So it wasn't just, these are at those areas where we changed the building a little bit in the geometry. And we had some interesting moments here with the glulam. This, I just want to point out, protection, right? So we want to make sure other trades aren't damaging this glulam that just went up. To Whiting Turner's credit, they would go around periodically and change the height of the protection. Why did they do this? Because of UV, right? Glulam will fade. So all this glulam is exposed to sun for an extended period of time until the building's enclosed, right? So they would go around and change this so we didn't get very harsh lines at the glulam. So I give them a lot of credit for that. Here, just shout out to Lyra again, we have these large open access stairs in the atrium areas, and they size the glulam to hang these stairs from the glulam. It's pretty cool, super cool. We introduced some skylights there, just to create some really nice light in some of these open spaces. Okay, diagrid, last one. And I know I'm going fast, but I have a lot to cover. The diagrid, this is kind of the jewel box of the Brigger project. Really terrific, amazing structure that Lyra came up with. Commons, again, is just a 3-story structure you're seeing here in the rendering. A lot of fieldstone. This is the vernacular of campus on Princeton, if you've been there. You're seeing the BioE building to the right, and then ES is over here. Large south-facing glazing, so we have a pretty sizable sun shading system on the south, and you're seeing glimpses of the diagrid beyond. 2 renderings of some of those spaces. This is a library space and a multi-purpose space. Some images taken during construction. This is really the first time that they finished putting on the diagrid on the 3rd floor. The diagrid here is 5 feet deep. It's really impressive. and we have these tiny, slender columns. They're solid, right, Mike? Solid steel? Yeah, solid pipes. Pretty incredible. Really amazing space. So the diagrid itself is made up of these deep glulam members that are sandwiched in between these steel fins that come out on these nodes. So wherever we don't have a column, that's a node, and then we have the columns here. Here you're seeing a connection to the concrete shear wall, which is the entire north wall of Commons. So you're seeing those plates, how they accept the glulam. And then all those holes are filled in with plugs. Image of a mock-up we looked at Structure Crafts facility, which was very helpful just to understand the geometry. We made some slight tweaks to some of the dimensions. And here is just the kit of parts that was shipped to Structure Craft and then shipped to Princeton site. Really cool. This is a finished image. I took this image last week. So one of the important things was to consider, and we'll talk about this a little bit more, is all the utilities that need to go throughout a space like this, right? So it's not a lab, okay, so we don't have to worry about laboratory gases. We kept all the ductwork out and fed it from the perimeter or from the floor. But in this multi-purpose room, we have lighting, okay? You have normal conduit, normal power conduit. You have emergency power conduit. You have sprinklers. We need a sprinkler head in every single one of these triangles, right? We have AV, there were speakers, drop-down mics, projectors, projection screens. So we had to make sure we had a path for, and you can see some of it up here, for all the conduit and for all the sprinkler piping. If you can see here, this little cutout up there, right? Typically the DLT would sit right there, but we have these 1 foot by maybe 6 inch high cutouts for all that conduit, for that sprinkler piping, so that we didn't have to drop anything below the diagrid. So it's really just an open view of the structure, which is really cool. The one interesting thing about the sequencing is as Whiting Turner was trying to figure out how they were going to put the sprinkler piping in, they couldn't do it after the diagrid went up. So they put the diagrid system in this state, right? They laid it, and before laying the DLT, they laid the sprinkler piping on top and then put the DLT on top of that. So pretty neat in terms of sequencing. Okay, considerations. Almost done. Sourcing, this is a big one. So when Lyra originally specified the timber for this project, we assumed we'd be getting all of our timber from North America. That did not happen. So Structure Craft, who was awarded the contract, they're based in Abbotsford, Canada. All their DLT, wood for the DLT, the dowels and the 2x, that does come from North America. So terrific. However, glulam came all the way from Austria at Hochschlager. Now the reason we use that is that Structure Craft has a very great relationship with Hochschlager, and Hochschlager's glulam is gorgeous. It's beautiful. A lot of the company, Eniad and Lyra and Princeton all went out to see their factory. For the DLT, they needed those glulam panels. That glulam came from Austria, so it had to ship from Austria to Canada. They had to get all those parts, right? They had to assemble pieces together, and then they shipped it to Princeton. Glulam for the columns and beams could go right to Princeton. So just something to consider. You may not be able to source all of your mass timber from North America. This project was too large, the schedule was too tight, that they could not find another supplier in North America to do this project. So because of the relationship they had with Hochschlager and because of the time constraints and costs, this was the setup. Now the LCCA that Atelier 10 did not assume that, right, early in schematic design. So the other things I just want to mention, North American versus European timber, there's different standards, right? America's ANSI, and then there's this EN 14080 standard for European timber. So what Lyra did as part of our submission to the AHJ in New Jersey was do a comparison basically of these two to prove that European standards and the glulam coming out of Europe either equaled or surpassed all the standards for ANSI, and it did. The other thing to remember here is if you're going for LEED, depending on what credit you're going after, and under LEED 4, there was a pilot credit that was called Legal Wood that did allow PEFC, which is the Program for the Endorsement of Forest Certification, over FSC. So just something, again, to consider depending on what you're going for LEED. Vibrations and acoustics. This is a big one, right? So we talked about steel in the labs. Vibration criteria for that was 2,000 MIPS or better, right? And that's in the steel zone. Outside of that, you're seeing in the darker orange, those office spaces where vibration criteria was lowered and even further lowered in these areas. And that gave us a lot of flexibility on size of the DLT, spacing of beams, things like that. What I want to point out here is that I mentioned that 3.5 inches of concrete, so it seems like an odd number. We started with three inches of concrete over a 1/2 inch acoustical mat, which was recommended by our acoustician. Whiting Turner, as they were looking at logistics and the sequencing of work, really pushed back on that and said, do we really need this? I don't want to, StructureCraft was not going to buy the acoustical mat, and they weren't going to install the acoustical mat, which meant Whiting Turner needed to bring another trade on to do that in the sequencing. So they said, hey, is there anything else we can do? And it turned out when we ran the numbers that just replacing that acoustical mat with an additional 1/2 inch of concrete gave us the same. So it worked out well. So we didn't have to change any, and this was during construction, right? So we didn't have to change any floor elevations. We simply just added more concrete. And Lyra, of course, checked in terms of weights, and it worked out fine. This, you're just seeing that, again, the timber here is shown in green versus steel. This is a big one, exposed infrastructure and utilities. So we don't want to put up glulam and then forget about all the stuff that's in the building. This is a lab building, right? There's a lot of stuff in the ceiling that typically would be above an acoustical ceiling. So we're talking about ductwork, laboratory gases, conduit, cable tray, all this stuff, right? And we were going to expose it all. So it was really critical that we took a lot of consideration on how these things would look. And that was during design. We worked with AEI, the MEP engineers, to really make sure the design intent was clear on our drawings. And we were coordinated to a point that it was realistic on what we were proposing, right? And also, this is an image from the Revisto model from Whiting Turner and their trade partners. Right? They modeled all this, obviously. And we wrote into our specs that they had to model conduit to a size down to 1/2 inch. So anything exposed in mass timber we wanted to see. And they submitted shop drawings for our approval. And that was important for us to understand what was going on. Chill beams throughout. Chill beams means ductwork and piping, right? So we made it even more difficult for ourselves. But what we did, you can see here, is really just, we struck a datum, right? And some of the lowest things here are the cable tray, the lights themselves typically were at that 10-foot datum, and you can see here as well. The chill beams and the adjacent light fixtures were all a custom color gray, kind of a dark gray. Cable tray and the conduit, we did not want painted conduit specifically because a lot of the conduit was attached to the other side of the DLT. We did not want the painters getting near there. We just did not trust them. And really the fact that it's just this kind of galvanized color actually looks like just another shade of gray, and it worked out kind of nicely. There's large bridge ducts that have to pass between some of these areas because our penthouses are split. So those are painted and wrapped. And then any PVC piping from drains, that was also wrapped in a gray PVC cover. So really important thing to consider. Penetrations, this is another big one. You saw images from Dan's presentation as well. Obviously, you're limited on penetrations. Like Dan mentions, it's incredibly important to have these figured out early because all these penetrations are done in the shop. So these are all with a CNC machine, excuse me. So some of the first shop drawings we got were DLT, right? And so Whiting Turner put a lot of pressure on the mechanical and plumbing contractors to determine locations and penetrations. We showed them on our drawings, but they need to be coordinated, make sure the location was right, make sure it worked, and that StructureCraft was okay with it, and the sizes were correct. The other thing we did here was we took advantage of some of these areas here. It's kind of non-critical zones. See this little slot here? We talked about all that lighting conduit. So we really didn't want those small conduits below the beams if we can help it. Obviously large ducts, we weren't going to create big openings, but any small conduit serving lighting, we took advantage of that, and they shoot through these spaces, and it worked out pretty nicely. It was a nice detail. Here you're just seeing some typical details from Lyra's drawings, just showing guidelines on penetrations in DLT and glulam. Not a very exciting drawing, I know, but just something again to consider: fire stopping and engineering judgments. The industry is still catching up. I think we'll find probably in both of our projects, if you had engineering judgments as well, Dan, I'm sure they'll be used on future projects, right? They're getting into that library, what's available to other architects and engineers. So we worked directly with Hilti during design to come up with some of the typical penetrations through DLT, but the contractors also relied heavily on Hilti to come up with some of these details for things that didn't exist already in a catalog. Lastly, sealing of adjacent elements. This is a section of the 2021 IBC, so it didn't apply to our project at the time. Again, we filed under 2018, but Jensen Hughes was aware of this coming, and so we considered it as a project and determined it was important for us to follow it. even though we didn't kind of fall into the categories of the construction type that it's mentioned. But really the purpose of this, if you can imagine in a fire, as that char layer begins to degrade on the glulam or the mass timber, you're potentially creating pathways for air or smoke that fire could travel from one floor to another. So what StructureCraft came up with, you can see here, these don't exactly match, but this is a typical detail for a larger connection. This is just a photo of something smaller, but here's that steel connection. There's a recess allowed for that, and then they filled that area in with this intumescent tape, which honestly I wasn't even familiar with, but the tape will expand when exposed to heat, right? So it can, as the timber starts to erode, it can help to fill that gap and again prevent the passage of air. Pretty cool. Okay, I'm almost done, like 3 slides. This is just, I like to just compare renderings to the final condition, see if we got it right. So this is a rendering of the ES atrium. You know, in addition to mass timber, and if you can think about the type of research that's going on in this building, environmental studies, geosciences, the High Meadow Environmental Institute, ecology and evolutionary biology. They were really excited about using materials inside the building that reflected the type of research of what they're looking at, right? So in addition to mass timber, we have polished concrete throughout. We have these mass slabs of stone, both at the stair plinths and at the walls. And here's a picture that was taken just last week. So pretty similar, right? This is an art space beyond. You're starting to see into those upper levels. Down here on this level, we didn't have any large bridge ducts going through, and we were able to keep air supply at the perimeter of the space. So we really were just left with conduit serving light fixtures and sprinkler piping, which was really nice. And then finally, just another image taken from an aerial. This is from the northeast looking southwest. So now this is the Theorist Pavilion, that small two-story space that has a mix of DLT and steel, and then BioECs, commons, and then ES stretching out. That's it.
So, thanks, Matt. I know that this was your first mass timber project, but it doesn't sound like it. Here's some resources also for Princeton. There's also INEAD's website as well as Princeton's website, but also we have Princeton symposium coming up in November 14th. So please join us there for a physical walkthrough of the campus as well as discussing the overall campus sustainability efforts. And then UMass also, the Perkins Eastman's website, and then UMass as well. You have a Instagram also. So exciting news. We wanted to leave time for a little Q&A, and I'll also open it up for the audience. But can we turn on the lights? And you want to grab a seat? So I like the fact that there's a contrast of public and private institutions here. I know for UMass, it was driven by the chancellor's sort of charge. However, what drove Matt for Princeton? What drove Mass timber?
Yeah, I mean, as you guys hear me on the mic? Is that better? Hello?
Can you hear us?
Can you hear us? Okay.
Did you hear the question? I said that UMass had a charge from the chancellor, and what drove mass timber with Princeton?
Yeah, it's a great question. You heard me mention before that it wasn't a hard sell to Princeton. They were really excited about using mass timber on this project. And as I mentioned, there's several projects that are already complete and still under construction that are also using mass timber. When you think about the scale of Princeton, most of the buildings are 3 to 5 stories tall, right? They're not building high rises, and it's appropriate and allowable to the building code to use it. For ES and C specifically, as I just mentioned, it's reflective of the type of research that's going on. So they had the support from the researchers themselves. They were excited to see that. I was on site just last week and ran into a researcher up there, and she was just marveling at the beauty of the wood and the space. It's very different from what they're coming from, so it was a nice change for them. And so again, it wasn't a hard sell in terms of cost. The LCCA bundle that I mentioned worked out from a cost perspective, and we got additional funding from their sustainability committee, so it worked out great.
So Dan, with UMass, the public procurement process, I'm sure it's very different than the private procurement process. And could you describe a little bit more about that?
Yeah, I think that the first thing to note is that we were awarded the design of the project at the same time you issued construction documents.
Is that right?
Yeah, and we're finishing about the same time. So
how big is your project?
So it's 100,000 square feet. Okay. So I guess I'll withdraw that comment. The other thing is that everything that we specify, it needs to be publicly procured, and in Massachusetts at least, that means we need 3 suppliers for everything that we do. Absolutely everything, or we can have a bid protest. So we also were bidding mass timber. We didn't know and couldn't direct the species, or we would have ended up having to procure it differently. So actually we had the structural engineer designing to one species, and different manufacturers were offering it in different species. So we actually didn't have control over that at the end of the day. So those are some of the pieces. In terms of the integration of mechanical systems, in Massachusetts there are 13 filed trade bids. So even though we're procuring construction management, the trade bids, electrical, mechanical, all of these systems that you want to integrate are low bid contractors. So it doesn't mean it can't be well coordinated, but it means that there's not a collegial, collaborative environment that can be set up because it's low bid, and anything that isn't coordinated is subject to change order.
Yeah.
So-
I like mine better.
Fair. And it's bigger.
Yeah.
I
It's
hear
bigger.
it.
Yeah.
But it's not bullying.
Princeton is very, very rationalized. However, UMass has, let's say, it's an addition, it has site considerations, it's not prone to sort of more typical mass timber construction, Jamie. Can you describe a little bit more about some of the design challenges?
Yeah, I mean, they occurred in plan and section. Dan sort of mentioned, I mentioned the clear geometry and plan that was a challenge, in spite of our ability or our efforts to try to rationalize the research footprint. And we played a similar game that you guys did where the geometries get torqued. That's sort of where we freed ourselves to put program that was less driven to an orthogonal regime. But we did end up needing to solve structural dilemmas that occurred at those conditions, and there were plenty of them. But we also were limited in height because we were tying into the existing building. So where we ran into difficulties coordinating infrastructure with limited floor-to-floor height. It's kind of fascinating we didn't celebrate the existing building with a photo, but there's not much to recommend it. But I think the goal at the end of the day for the occupants was to allow the 2 buildings to come together as one. And I think hopefully at some point there's some interior changes to the existing building that help achieve that aim. But yeah, I think there were challenges that I think had some of us and perhaps the client scratching their head a little bit initially about the feasibility of this building going to timber. But the hybrid technologies allowed us to solve some of the larger spans and to accommodate the change in topography with the foundation wall. And we sort of embraced the idiosyncratic structural solutions that emerged that you saw in some of the photos. And some of them got hidden. A lot of the structure that we had hoped might be exposed ended up with ceilings, driven by the client's preferences So all of that, when you sort of take it together, leads me to believe that in the future, I think it's not as heavy a lift, I think, as some of us may have expected. And I believe the sales pitch going into something like an interview to say, you can do this, I think you can. You can accommodate a lot of these challenges in a way through this process we learned are achievable. Yeah.
As we know, PIs like to make changes. How are you dealing with some of the flexibility and changes at the last minute or in construction?
Yeah, the ES project right now, we're in that phase where PIs are moving in, and they're either telling us we got it wrong, or they don't remember telling us that they asked us to do a certain way, or frankly, the research has changed, and there's a need for something different. So it's difficult right now, specifically for Bridger Hall, because researchers need to move out of their existing space very quickly because there's other projects that need to happen in those existing buildings, other renovation projects. So, however, as painful as that is, I think it's testament to the project, specifically AI, with sizing the systems appropriate to accommodate the kind of requests we're getting, right? So different temperature and humidity set points in labs. Maybe that a particular piece of equipment needs a little bit more space, or we need additional laboratory gas drop for something. And I mentioned those corridors where the primary kind of umbilical for all the lab services are, and by bringing those into the entries of the labs, Whiting-Turner can simply cut off something, shut a section down in order to add an additional drop or something. So I think it's, and I'm curious what you think about this, Dan, you have to be careful not to oversize your MEP systems, right, for future flexibility, but you need to size them in a way to provide some flexibility, because energy is still incredibly important. You don't want to go overboard.
For the computer science building, we thought we had a fairly low-tech kind of laboratory. But what happened, even in the short time that we were designing and building the building, is that AI took off in a way that really wasn't expected. In fact, we spent a lot of time talking about power and data requirements for computers. And we have a research data center in the bottom of the building, which is meant to house a lot of the workhorse processors for computer science. And if the requirements went beyond that, it was going to be essentially cloud-based in the university data center. Fast forward only about 2.5 years with what's happening with AI and research, and a request was made during construction administration. Could you please double the amount of circuitry to every lab bench in the building? So luckily the head end was okay. It had the flexibility, but circuitry distributed around certainly didn't. Basically, every student wants to be able to have a graphic processing unit, a gaming computer, basically. There's enough capacity for cooling, but actually the placement of ceilings in some of those areas in some ways made that more possible, because they could work above the ceiling. So.
Before we open it up for questions, I'd like to acknowledge, as Dan and Matt and Jamie are representing a broader team here. There's a broad team here for Perkins Eastman. Can you just stand up? Because, ultimately this is a team sport. There's a whole sort of slew of
Andrew
technicians and
Michael.
designers involved in the project. I wanted to acknowledge them. And then from INEAD, from the Princeton project, even Lyra.
I don't know if I convinced anyone to show up.
Well, to Matt's point, they only told their firm today. But there is a broader team here that is part of the success of the two projects. And I'd like to open it up for Q&A for anyone who has any questions.
Vivian.
Yeah. I think a lot of COT that you use is softwood COTs. Has there been any exploration using hardwood COT? Because I know that in the US now there's some research going on using hardwood COT, such as beech or yellow poplar. Has that come up at all during your conversation? And also another question about, and I think the sourcing information that you shared, Matt, I was surprised to see that there's not any US manufacturers. You know, somewhere I think there's some Tennessee manufacturers out there. Why do we have to go all the way to you, not we, but you know, Austria, in terms of obviously this the issue of embodied carbon?
Sure. Yeah. No. You want me to go first? Okay. So in terms of species, I mentioned we tried to get Doug fir. It was cost prohibitive. So the only alternatives that I recall that StructureCraft offered that were a lower price point but still an attractive species were spruce or spruce pine fir. We didn't talk about poplar that I remember. Mike, do you remember? No, I don't either. Yeah. Sourcing, yeah, it was a surprise. We were really hoping for a North American contractor and supplier, but there wasn't one. At least Whiting Turner couldn't find one, and StructureCraft, with their relationship with Hochschlager, really stood firm and said, this is the way we want to deliver this project to you. You're going to get the best value, the best product. And that opened up other complications in terms of using European versus North American timber from a code perspective, but we got beyond that. So the team was really hoping that we could have sourced everything in North America, and unfortunately, I think it came down to size and schedule.
Could you remind us when the bidding actually happened in terms of year? I'm thinking in relation to COVID.
Sure. The design assist package went out at 100% DD, which I have that graphic up there and now I can't remember. That was 2020.
So it was right around.
Yeah.
And was there an impact of COVID to the ability to source the material?
I don't know if timber specifically, but for a lot of materials, yes. Yeah, for sure. That was tough. Yeah.
For us, all of our bidders were North American. They were not hardwood. We ended up with timber from Canada, Eastern Canada. Don't jump to the conclusion that that's close, because you go to Montreal and then you drive 6 or 8 hours north of that to get there. There's some suppliers in the southeast and the northwest. So we were going to end up with North American product in any case.
And the year that you all sourced your material?
It started coming on site, let's see, 2020, early 2024 was it?
2020.
Oh yeah, no, 2024. I mean,
2024.
it was at the beginning of that. So design started in 2022.
And I think I mentioned this before. The DLT components were North American timber. I believe the dowels they got from the U.S., but the 2x lumber they got from Canada.
The Austrian movement was orders of magnitude cheaper than what we did.
Really?
The 3 bidders that you mentioned,
Mm-hmm.
StructureCraft was by far the cheapest.
Really? Wow.
Are you finding any difference in sourcing now that we're sort of?
We have a few mass timber projects. We have a few mass timber projects in construction right now. One is near your project at UMass. We got the same product that we used at Princeton there, so we're using dowel laminated timber. We did have some challenges with the the 3-bidder requirement of but they filed some paperwork so we could get a single source. But we are using European glulam for the Rock and Roll Hall of Fame expansion in Cleveland right now, and I think that came down to cost as well. So. Oh, sorry, I'm with Lyra. I was hiding.
So Steve?
I'm curious, we've done a lot of wet lab buildings. What would it take to do a wet lab building all in mass timber? And presumably at like a typical bay of 22 by 33, perhaps a zone of bays of 22 by 22, because it would be kind of a beautiful thing if you could do a wet lab building all in timber.
It would be gorgeous. I mean, just thinking of the sizing alone, what your floor-to-floor height would need to be just to provide your minimum clearances for all your utilities above those benches. I don't know. It doesn't seem, I mean, today it doesn't really seem feasible. I mean, we never considered it for Princeton, certainly. And you saw the lab modules that we were holding there. And that was, and I mentioned that detail, I showed a picture of that steel beam. In lieu of a standard W shape, Lyra designed a back-to-back channel with a concrete infill that kept it incredibly shallow. So you can imagine your major ductwork coming out of your shaft. Typically, you got to penetrate a W36 or a W30. This got really shallow. We could stay underneath it. And the other advantage of that is that concrete infill, we could core through it. So if you have a beam line on your wet bench and you have a sink in your bench, offers a lot of flexibility to go right through it. So, I mean, I'd love to try it. I would just be concerned about how tall the building would need to be just in order to accommodate those sizes for those spans, you know. I don't know.
But your main concern is about vibration.
Vibration and height, yeah.
Well, and the 100 pounds live load as well, or just the vibration?
I mean, vibrations were pretty tight. This was 2,000 to 2,500 MIPS based on what was going on there. I don't know. Mike, could we even do that? I don't know. Yeah. I mean, DLT, or would you have to go CLT with it?
We looked at it for the UMass project that I just mentioned. So very similar, they have sustainable aspirations. We looked at all different, I think we looked at 64 different framing combinations. They couldn't afford the all glue lamb scheme. That particular project, we do have a high lab floor. Floor to ceiling, I think or floor to floor 16 feet. So we could fit it there. What we ended up with was a hybrid structural steel framing system with the DLT planks spanning to it. That was just about economy. But I think it's about, as Matt said, floor to floor height. On that job, we could get it, but they couldn't afford it. So you can get there. That was a 2,000 MIP project as well.
With
Those
DLT?
Criteria.
Really?
With DLT and
Wow.
steel. In those particular lab bays, I think the span is, it's about 42 feet.
Wow.
And 42 feet, and it has a queen post truss system. So it's a 5-foot deep truss with DLT spanning 22 feet between those trusses.
An open truss that you could pass through with utilities.
Yes.
Yeah.
Yes.
Yeah.
You can't really see the truss when everything else is up there.
Right.
So it can be done. I think it's very cost prohibitive right now. Beautiful, sure, but yeah.
Do you think the cost margin would close the gap?
Maybe. I think there's all these competing interests, right? And we'll see what happens. But we did study performance in addition to cost. And it's funny, we studied embodied carbon versus cost. And it's funny that they pick the system that they want, right? The client, that is. We're not necessarily picking the least embodied carbon. So there's also this, style that we're looking for, right? That our clients are looking for, that we're trying to achieve. So that obviously plays a role too.
Next question?
Hi, I was just wondering, for the UMass project with the embodied carbon calculations, were those just of the superstructure, or did they also include the envelope glazing and substructure? And I was also wondering for both projects if a great benefit with timber is that you can reuse the components at the end of life, so it was designed for demolition, one of the design factors as well.
Yeah, good questions. The study that we did looked at everything in the building to finishes. So, I mean, it's an interesting moment because right now there's a certain amount of literacy around energy use, kb2 per square foot per year. People don't even know the units for embodied carbon sometimes. And then also they're talking about, like, where's the baseline? What is it? So we used various baselines and compared them and looked at both the biogenic and the non-biogenic parts of carbon to understand if you're thinking about the embodied carbon in the wood, and et cetera, and also what happens at the end of life if it decomposes. So there's like there are these arguments that can be made. Those energy and carbon are crossing over, well within the lifespan of an institutional building. So and the other thing about it is that it's benefit that comes to the environment now, right? So if you have to wait for a decade or 2 decades, and you're talking about 2030, 2045, you're not getting to the crossover point.
Yeah.
So it has to be low embodied carbon, and it has to be now, if that's your goal, and that's what you mean, right? So then, replacing a significant part of the structure with high embodied carbon, isn't helping your other goals. As far as disassembly, the building's not really made for disassembly per se, in part because they're both fire rated and they both need to be covered over. But a carpenter could set us up for disassembly probably by drilling in if they understood the details of that. But it's not per se meant to be easily disassembled. But it will be there for 100 years.
Yeah, I mean, certainly for Princeton, our hope is that they will continue to renovate versus decide to demolish, right? And our intent was to create as flexible as a floor plate as we could to allow for that. So as simple as, again, going back to that laboratory module, which I think is just super critical when laying out a laboratory, it can also be very flexible, right? When you carry that lab module from the wet lab across the corridor to these non-lab spaces, 2 offices can be a conference room. 3 offices can be a group desk for students, right? That's the idea, right? And even within that lab, that large wet lab, maybe it's an open lab today, but a new PI is hired and I need a tissue culture room. It's not so hard. We can do that, right? We can work with that lab, that module, put up several walls and put in a biosafety cabinet and whatever gases you need, and we're good to go. And on the C side, it was interesting because almost the entirety of the 4th floor of C's is shelled laboratory. BioE is a relatively new department at Princeton. So they're thinking long-term growth. They're currently recruiting, and we're in the process now of meeting with new PIs and figuring out what's required for their space as they move in over the next year or 2.
Thank you.
Thanks for the presentation. Both projects have really beautiful details. And you both kind of mentioned that both offices are relatively new to mass timber. I was wondering if you could expound a little bit more on your collaboration with contractors, vendors, and the people who perform design assist. What were those conversations like, and how many of those beautiful details were actually from those conversations or actually produced internally by your architecture team?
I mean, I'll take the first piece about new to mass timber. I was just mentioning that the first mass timber building that I consider mass timber that I designed was completed in 2008. It was glulam columns and beams, very much like what you're seeing here, not much different. In fact, many of the systems are similar. What was different was the decking was solid wood decking. And so it was put together with 3-inch pieces of wood. They were slid together, attached to the beams, so they weren't laminated, doweled, or nailed, other than to the beams. The process that you're asking about is really important because we can draw some beautiful details that you can't build. And so working with people who are doing that 24/7 is really important. And so we were lucky to have a builder that has been doing a lot of these in New England, and also with the selected manufacturer of the harvester, actually, because they own their own timber, and manufacturer and design assist person. So there are lots of conversations about it. Really, actually coming from doing a lot of public procurement, it was a delight because they were on board with doing that.
It's a matter of trust, right? Trust in your partners.
A matter of, yeah, absolutely, and being open to learning about what works well for them. So.
Yeah, when we started the design of the Princeton project, I don't think we knew that there would be design assist for mass timber. We assumed there'd be for the curtain wall, most likely. Whiting Turner for New Jersey, there were heavy VE exercises for this project. We had a strict budget, we had to meet it. And at the end of each phase, there was a big VE effort. Whiting Turner was struggling to get trade feedback. And they suggested to Princeton and us that bringing on design assist contractors could help with that VE effort, right? These guys know how to find efficiencies and find cost savings. So that was one of the primary advantages of bringing StructureCraft on, was finding ways for cost savings, right? They had recommendations for DLT sizing and simplifying connections, things like that. The design was Lyra's, right? Lyra designed the structure. And it was important to us that they maintained control over that. But StructureCraft in the end was a partner to help develop some of those typical details. They made suggestions even on the diagrid. They brought forth some ideas on how they could change things. But that particular system, it was really important that Lyra maintain control of that, and then they did. But yeah, I think in the end they were a good partner. Was it the perfect relationship at the start? No. But I think they seemed to hold back a little bit before they were really awarded the entire project. There was still an opportunity. Princeton retained the right to still go out to bid, back out to bid for timber with the CD package. So once they were on board and they had that contract, I feel like the relationship got a little better. We went out there, we met with the team, we saw what they were doing, and it was, I think in the end, really a great relationship and very helpful.
One last question.
Go ahead. So often enough with these projects, the realities of economics and life come in the way. For example, like those windows, photochromatic or whatever they're called. What are some experiments or like some design, fun things that you guys wanted to do, but that the project's constraints or the realities or just things that were not right, it wasn't right for the project. What are things that you guys missed out on that, somebody like me who's got all the free time in the world to do this and access to fabrication labs, could you guys like guide me towards experiments that are worth exploring, at least on the, for myself?
Yeah, I guess maybe relating to your question about what did we kind of want in the building that didn't quite get into the building. I think the story of a net zero building that was producing its own energy, so like renewable energy on site. We first of all love the idea that there was a geothermal component, but it's in the project, but it got pulled out of our scope in a way. So we didn't feel intimately connected to the geothermal bit. However, the school was committed to it. So that was okay. I think what I kind of regretted missing was the photovoltaic component. We had the skylight, we had an idea that from within the atrium you'd be able to sort of witness that. As a subtle irony, the adjacent building has PVs on its roof. Its only redeeming feature for that building is a PV array that no one could see. No one knew it was there. But now the top floor of our building you can view it. So we didn't provide the PV array, but at least we provided a view to it. So the building is PV ready. Hopefully at some point, they can come in and do that. But that wasn't part of the project. I think there was also, we didn't get into this, but one of the early changes in the design of the building had to do with a movement of a road. Part of the challenge that we had with the trapezoidal shape was accommodate the road that was right there. Early on, through schematic design, we moved the road. So moving the road opened up all different kinds of conversations about what the building could achieve internally. And then at the end of SD, they said, we're not moving the road. So what that led to was constraints that we had to resolve, but also, and maybe Dan, you can speak to this, and this was actually maybe one of the positive changes that came out of that was we pulled the whole penthouse off the building. I'm not really honestly sure how we did that. Dan, could you shed some light on that?
Well, part of what happened was we had to tighten our belt in terms of the site. And by the way, this is not going to answer your question, but it is an interesting question to answer. We had to tighten the building up in terms of its footprint because they decided it wasn't worth moving the road. But at the same time, they also decided that the ground source wells would be part of a district plant, which meant that the heat pumps that went with that came out of the building. So then we had room to put the air handling units into the building. And so there was some push and pull, and we had the same schedule as we had before, but we had to redo schematic design and rearrange a bunch of things. But maybe to answer your question, I think for me, what I just said before was that there were some ceilings that allowed for some flexibility around power and data that changed before the building was even opened. And that was a bit of a heartbreak for me because I imagined lots of open spaces. But there are a lot of clients on a project like this. There's a university project manager, there's a university planner, there are a lot of people to, as you know, at UMass Building Authority, a lot of people to take care of. And that was one that fell out that I will miss. I mean, it's not an atrium, actually, the multi-story space is very woody, biophilic.
Smells.
It's gonna smell beautiful and be quiet because of the radiant heating, but some of the research and office spaces won't have quite as much of that as I wish it would have.
So my challenge to you would be to figure out how to use mass timber construction without having to put concrete on top of it to tamp down vibration.
And she's going to come back and follow up on that.
Yeah, don't go there. Give him the challenge.
Worst comes to worst, I get a good portfolio being started with, so I'm not going to be mad about it.
I want to thank everyone for joining us tonight. I know we have to wrap up. It was a pleasure for us to present our work to you all, and we're really glad you joined us today. And yes, keep the challenge of using mass timber out there, keep pushing the boundaries, and let's keep using it.
And this was a result of a conversation, I think, maybe 2 years ago, when we started to discuss use of mass timber in science buildings. So as you start to, as codes are changing, people are learning, this is sort of a learning opportunity, and then it gets only better by you. The next generation will build sort of faster, stronger buildings. So thank you. Thank you for joining us, and appreciate you.